talking about for clubs.
Oh,
You're
for
welcome.
clubs, not
Money
No, not for like scholarships or anything. No, nothing fun.
I need $12 for some markers.
You're gonna have to send a memorandum. For
Just
that.
just random requests.
You're like, yeah, I don't.
Speaking
I didn't want you to
So-
be
I think we're ready.
By the way, lecture 2.4 is on sampling. Yeah.
Let's go.
So,
read us like a little bit of it here and there, just sort of.
just a sample, just a sampling. Yes, I'll try to do that for you. So while most quantities are continuous, making them naturally represented by continuous functions, in order to represent a signal in a computer, it must be given a discrete representation. Okay? That's what this whole thing is about. So constructing a discrete representation of a signal is called sampling it. A numerical value is assigned at discrete values of its domain. Okay. Since the quintessential signal has time as its domain, we will henceforth speak as if it is the only type. So, time domain signals are like typically what we're sampling. But technically, you could take a signal across a spatial domain and whatever. But we'll typically think of it as being a time domain sample. Okay. So consider a function. This is where the math part comes in. Consider a function f, which has as its domain the real numbers and as its range the real numbers. So it goes from reals to reals. That's what this notation is. Have you guys seen that notation before? F is a function. Somebody who's been in my class has seen it. Okay. So technically, oh, you guys use it in linear? Cool. So you read this as f is a map from R to R, from the reals to the reals. And so this colon is a map. A map is like a generalized function, but for us it's actually just going to be a function in the good old-fashioned sense. Okay. Good. So f is a continuous function of time over the interval t1 to t2, sampled at a constant interval t. So big T is going to be our interval for our sampling to form a sequence of real numbers that's denoted f sub n, where each n is one of the counting numbers, so non-negative integers. So a sequence would, for instance, be 1.2, 4.3, 62, 1, etc. That's a sequence. There's an order to them. They're not like necessarily are they in like alphabetical or magnitude order, but they come in a spatial, or not spatial, a time ordering. Like this sample was taken first, then this sample, then that sample, etc. So unlike a set, so a set has the squiggle brackets, right? A set with the same values in it, there would be no order implied by the listing of them. When you have a sequence, there is an order to them. All right?
even if they're the same values, though?
Even if they're the same values, yeah. Well, because you could be measuring 3 volts for a while, and then you could be measuring something else for a while.
Oh, I see.
So, yeah,
So it's relative to time.
it's relative typically to time. Most of our signals will be time domain signals. So we're going to sample it like maybe 5 times per second. And so our big T would be equal to 5 seconds.
I just want to make sure, so a set would then just be a series of, I don't want to say series, but careful definitions, but series of numbers that are not really relevant to each other or anything else. It's just a series, a set of numbers, correct?
So a set is unordered. It's just a group of numbers that has no order to them.
Okay.
A series has an order to it. Yeah.
Okay, thank you.
So a typical definition of an array or a vector, also it's a sequence of numbers that it has a specific order to it. So they're homeomorphisms, like they go back and forth to each other. You could construct a vector from a sequence, and you could, but if you had a set, then you wouldn't know. You could construct a sequence from it, but you'd have to decide what the order was. It wouldn't be defined. Okay, so good. So we have this sequence of real numbers of length n, which, since we already defined the time interval and the interval, our sampling interval, then the length of it has to be related to those, and this is how it's related to them. It's the difference in the two ends in the beginning time divided by the sample rate plus 1. That's that extra hanging one on the end that you have to get. Okay, so this sequence is called the sampled sequence, defined as follows. So each value of the sample sequence, f sub n, is equal to, it's really not surprising, f, so the original continuous function, evaluated at, so t1 is the first time, right, the initial time, plus nt, right? So if you're taking like the 12th sample, n would be 12, and you would be 12 sample periods in, and that would evaluate the function there, and that's what your fn is. So far, so good. And I think that sampling is something that makes a lot of sense to us. Like, oh yeah, like you've got a continuous signal, like a voltage, and you just take the sample, take a sample of it every, 5 times a second, which it would be 1/5 of a second. Earlier I said it would be 5 seconds, but that wouldn't make any sense. So 5 hertz is what I meant. So yeah, so this is our sampled sequence values, and we can think of it physically as being just like that process where you just take a sample. I mean, you could be looking at a dial that's moving back and forth, and you're just writing it down. Every time your timer goes ding, write down the value. Like you can do it manually. You could have a microcontroller doing it. Lots of different options. So we represent the sampling process as the multiplication of the continuous function f by the Dirac-Combe function s, defined as shown here, as the sum of a bunch of Dirac delta functions. So this is the Dirac delta, and remember the Dirac delta function, it's 0 everywhere except at time equals 0, it has this pulse, right? Where it's actually not defined, like the function evaluated at that point is not defined. It's like infinitely high pulse, but we say that it has an area under it of 1. So if you integrate over the Dirac delta function, you get 1.
Is that, when it's an infinitely high pulse, is that like the mathematical calculation from Gabriel's horn kind of thing, where when you do the integral, it's like an infinitely long, or in this case, infinitely high pulse, where the total period is 1?
I don't know this integral.
I've done this one.
Gabriel's horn?
Gabriel's horn, where it has like a finite, what is it? It's a finite surface area, but the volume is infinite, or
Yeah.
it's better. Maybe it's
I think it's the other way around.
Hmm.
Yeah, it's a really weird integral when you do
yeah,
this.
sorry, because
the surface area is infinite.
Wow.
Yeah, it's really cool.
Huh. I haven't encountered that.
So I'm just trying to.
I mean, maybe it's in there. I don't know. I mean, this function was used a lot in engineering for this type of thing, and it's also used in finding responses of systems to like a sharp input, like a spike input. So if you were to take a hammer and whack something with it, you could approximate that with an impulse with a Dirac delta function. So there are some other uses too. It comes up a lot, but I figured you guys would have seen it somewhere, but I fortunately am going to slow down and discuss it a little bit. So
Well, that's why I brought up Gabriel's form. I was curious if it was the same thing.
yeah, I mean it's defined as being 0 everywhere. At time equals 0, it's not technically defined, like it doesn't evaluate to anything finite, but it's sort of considered in the distribution sense of there's an integral across it that's defined, and that integral is 1. And if you scale it by any factor, so if you do like k times delta of t, then clearly there's still no defined value at 0, and it's still 0 everywhere, but the integral, the area under this this spike or this pulse is considered to scale by k. So it really only has a strict meaning when it's integrated over. And when it is integrated over, it has this really nice property that we're going to talk about today called the sifting property. Sifting property. So we'll get there. But in any case, what a Dirac delta, we often will draw an arrow on this because it's just like infinitely high spike there at time equals 0. So whenever when we see this, what this is a sum of, so when n equals 0, this is just the Dirac delta function. Boom. When n equals 1, this is just the Dirac delta function shifted over by t, right? And then when n is 2, it's shifted over another t. So at every sample point in time, you're going to have a Dirac delta function there. That's what the Dirac comb function is defined to be. So we illustrated it in figure 2.3, so that's on the next page here. This top figure, this is the Dirac comb function. So it's just a bunch of these Dirac deltas that are spaced out by t, by the sampling period. Okay? And you might ask yourself, why are we doing this? Like this equation 2.27, that was so intuitive. We totally got that. Why are we talking now about these weird distributions, these Dirac deltas that don't have a value, but there's an integral? I'm hopefully going to motivate that a little bit at the end of today's lecture, or maybe it'll be on Friday, when we discuss the Fourier transform of this. We're trying to come up with a continuous representation of this. So I'll explain more as we go. But I will say that there is a point to doing the math. It just might not be apparent up front. So this sampling representation yields the sampled function, which we use f star to denote, which is a function defined as follows. So the sampled function we define to be f star. I guess I should just try to draw like a star. Kinda. Gotta draw it lighter. There we go. F star. Not too bad, right? Of t is equal to, so you take the Dirac comb function, this guy, with all of those Dirac deltas in it, and we multiply it by the function we're trying to sample. Okay? Now, this is, we can plug in what S is equal to here. So this is the definition, but we can expand it and see what it looks like. So we have a sum from n equals minus infinity to infinity of delta of t minus nt times f of t. Okay, so this representation requires some interpretation. Recall that delta is 0 everywhere in this domain except at t equals 0 when it is undefined, but has an integral over the pulse of unity. So if you integrate over that pulse, the peak, you get 1. Unity is 1. Further recall that scaling delta by some factor lambda yields the same functional value, but is understood in the distribution sense to be multiplying the integral over the pulse by lambda. Okay? We call this the pulse strength. So the sample sequence values Fn are computed from F star by the following equation. So sampled sequence values from F star.
Double siding is a thing.
Yeah, I couldn't get it to work in the minute and a half between having this finished and getting to class. So we're going to integrate for the nth sequence value. We'll integrate from, so that Dirac delta is going to happen right at nt. So we're going to integrate from nt minus to nt plus. Okay, so we're gonna say, oh, okay, well, we can integrate over 0 all we want, and we're gonna get 0. But the only place that it matters is the integral over the pulse, right? So we're gonna integrate just over the pulse. And if we do that for f star of t dt, that's what our sample value is going to be. So remember, our sample value is also what we get from back up here if we just evaluate the original continuous function at that given time, right? Evaluate that function at, say, t1 is just 0. At like the third sample, it would be n equals 3. We would get f of 3t, the third period in. We're saying that you can get the same value if you have f star, which is the sampled signal, but you have to integrate over the pulse to get that value out. So that's equal to f of t1 plus nt, which is the original expression we had. So these two are the same. You can compute them from each other, but typically we think of it in these terms as being like the intuitive one. This is there for the mathematical niceties that are going to come, but for now it's just like annoying, but there is a point to it. Just have to trust me for now. In other words, we integrate over the nth pulse to get the sample Fn. That's the mathematical representation. Okay. So let's take a look then at this. This figure took me a long time to make, and it's so worth it. Thank you. So, this figure is the Dirac comb and the function that we want to sample, and then the sampled function. Okay? So it shows us kind of all the things. Now we take our Dirac comb. Remember that our sample period is t, so these things are spaced out at t, and we multiply it by our function f of t, right? And all of these pulses had strength 1 when they were just part of the Dirac comb. But when they get multiplied by f of t, they take on the strength of whatever the function value was there. And we represent the strength by the length of the arrow, the length of the stem plot arrow. So these are, I didn't put a scale over here, but these values are now what the strengths are of each of these pulses. Okay?
So this equation isn't linear then, because it's not, because the strength is 2t, but it's not, oh wait, that's not the, on the bottom chart, it's not, each strength is based upon individual circumstances, it's not like it's saying that the strength is 2t, correct?
So this is denoting the sample that we're at in time. So we're at 0, and then we're at 1t, which is our first sample time. So I'm just saying, instead of having t1 here, the beginning of our interval, I'm going to call t1 0.
Okay.
And then every sample that you take is taken at t and then a multiple of t thereafter. And so then the function values, so let's say, for instance, that this point right here on f of t was equal to 7.1. Okay? 7.1 was what f of t evaluates to at 3t. Okay? What we're saying is that now our sampled function, f star, which is defined by all of these scaled Dirac delta functions, has its 3t pulse now has strength 7.1. So that strength means that if you were to integrate over an interval, I mean, really you don't have to be right up next to it because everything all around is 0. But if you integrate it over that interval, for instance, you're going to find the area under this pulse. Everything else is 0. The area under this pulse is going to be 7.1. Whereas the area under this pulse was just 1. All of them, the areas under them were just 1. But now that they got scaled by this function, now they take on strength associated with the function values. Okay? I mean, I think that it makes total sense. It's just like, okay, why write it in such a complicated language like LaTeX? I'm the reason for that, by the way. I don't know if you knew. You can blame me for that. You're welcome. I'm sure that you probably already knew that. Okay. So we're feeling pretty good. We get, representation of the sampling where it scales all these Dirac delta functions. We don't really know why that's useful yet, but it works. And if we wanted to get out an Fn for any of these pulses in the sampled function, f star, all we would need to do is integrate over the pulse, and we'd get the associated fn for that pulse. Okay? Okay. Good. Now I'm going to take us on a tour of the spectrum of a sampled function. Now, this is where it starts to kind of get interesting, the way that we set this up. And it'll continue to be more and more interesting as we go. So the Dirac-Combe function, S, is periodic and therefore has a Fourier series representation. Okay? From 2.2, we can compute the components. This is the Fourier series section. Definition 2.2. It was Fourier series, and it was the complex form of the Fourier series. So we can compute the components of the Dirac-Combe function. We call the component Cn. Well, actually, C. There are positive and negative n, so C plus minus n equals just plugging the Dirac-Combe function right into the formula, 1 over t times the integral from minus t over 2 to t over 2 of s of t, the Combe function, times e to the minus j 2 pi n t over t dt. Whew. Okay. So that's our expression. And I think we can all agree when we look back over here, this continues on forever. So if we pretended for a moment that this was the 0 times 0 pulse, then from minus t over 2 to t over 2, you only have one Dirac delta function in there, right? So we're integrating over only one period, so we can eliminate all the other Dirac delta functions from contention, this big sum that defines this. We don't have to deal with any of that. All we need to do is say, oh, this is just 1 over 2 times the integral from minus t over 2 to t over 2 times the Dirac delta function. Because that's the one that shows up in that interval. It's not time shifted at all because we're doing it about 0. So conveniently, all right, so that is the expression. Now we're going to actually take an integral with a delta function in it. And now we're going to use this nice sifting property of the Dirac delta function. Okay, it states that, and this is used a lot and proven almost never anywhere. But I do think that it's pretty apparent from the definition of the Dirac delta function how to do it. But I'm just going to state it, and we're just going to go from there. There's some mathematical detail that I'm going to kind of gloss. So the Dirac delta function has a nice property called the sifting property that states that for some function g, the integral over some interval I of delta of t minus tau, so the Dirac delta function time shifted by tau, times g of t, so some function, dt, is just equal to g of tau. So that time shift, you just evaluate that function g at that time shift value, and that's the value of the integral over the interval I, and technically it's 0 otherwise. And that's the part we're going to gloss. I'm going to give you like a hand-wavy argument for why we don't have to worry about that. But what that means is when you see a delta function in your integral, what you need to say is, hooray! Don't have to do much of anything. You pretty much just get to grab whatever else is in there with the delta function, and that's your integral. Just evaluate it at the time shift, and you're good. So, that's what we'll do. So, C plus minus n is equal to, this is our function that, this is our sort of g as we talked about it down here. So what is the value? So we've got our 1 over, I don't know why I wrote 1 over 2. It's 1 over t. So we have our 1 over t still. And then this integral just becomes at time equal, so there's the time shift is 0 in this case, right? Ta is just 0. So we just need to evaluate this function at time equals 0, which is just e to the 0, which is just 1. Man, that got simple fast. So that was great, right? That was nice. So we discovered that, remember what we're computing here, these are the Fourier series components, right? And they're all just 1 over t. Not too shabby. We happened to choose the easiest interval over which to integrate. When time was 0, that exponential was pretty easy. But the same holds for any other period. So you could do the same thing for any period. Integrate over that Dirac delta function. And it does always come out to be 1 over t. So that means, this is the hand wavy part. Remember that it only holds for whatever interval you integrated over, the sifting principle. So technically, like, you'd have to do it for every one of these pulses in order to show that over the whole interval, everywhere that you compute this integral, this solution is valid. And I'm just going to say that it is. I'm not going to show that. But it's true. So the Fourier series synthesis is, remember when we do our synthesis, we add up a sum of all of these components. So S of t is the comb function that we're trying to reconstruct, right? Is 1 over t. This is just from the definition of the Fourier series synthesis for complex form. So n equals negative infinity to positive infinity. We would typically put in the CNs here, but the CNs are all 1 over t, so we'll just pull it out front conveniently. And then all we're left with in here is e to the j 2 pi nt over the period t. Okay, so we've computed the Fourier series for this. When I say series, does Siri think that I'm saying Siri?
Yeah, nobody loves you.
Siri says, she thought that I said, "Hey Siri," is for the app.
I don't know what you mean by the app.
Oh, you guys, I have British Siri. Hey Siri. What was that?
I don't know what you mean by the app.
There's also an Australian Siri, but I feel like British is best. And there's also male voices, but I like the female ones.
Unless it's like something funny like Mr. T or something. I don't know. Here's what you found.
Okay. So let's finish up this lecture. We're almost there. It's gonna be so fun. I think this is really cool stuff. So All right, so we have the Fourier series representation of the comb function. The spectrum f star of omega of a sampled function f star can be found directly from the Fourier transform, and I needed to rerun my LaTeX to get this is an equation number definition of the Fourier transform from a few lectures ago. Good. So let's go ahead and just, what we're going to do is we're going to just plug in this S of t, well, not just the S of t. We're going to plug in f star. So we want to know what the Fourier transform f star of omega is, which is the Fourier transform of the sampled function, right? And we are going to say from the definition, that is just the integral from minus infinity to infinity of f star, this is the sampled function, e to the negative j omega t dt. Okay, that's just the definition. When you want to find the Fourier transform of anything, in our case, we want to find the Fourier transform of f star, you plug it into this integral and compute the integral. Or you look it up in a table. Those are two options. So f star, by definition, is just s of t. That wasn't a very good s. S of t times f of t, right? The product of the cone and the continuous function we're sampling. E to the minus j omega t dt. That we're going to expand and make look really ugly, because the comb function has, we're going to plug in for the comb function, which from up there, we're going to plug in the Fourier series representation of the comb function, okay? So n equals minus infinity to infinity. The sum is over e to the j 2 pi n t over t. That was all s. And then we have f of t e to the minus j omega t dt still. Right? And nothing like having an infinite integral over an infinite sum. But now I'm going to make a move that I can't completely prove to you on the fly is a valid move. I'm just going to posit that this is true. This is another one of those steps that requires some pretty complicated mathematical inquiry to make sure it is a valid move. So if you were doing this derivation for the first time and you wanted to do this, you would need to sit down and think pretty hard about if this is true or not. Look up some of the theorems around this. But in certain cases, you can switch, a lot of cases actually, you can switch the order of the integral and the sum, okay? It isn't valid all the time for everything, but I'm going to say in this case it is, and we're just going to do it. And the other steps all make sense, and we could study this one move for a whole class period, and I don't want to get into that, so. All right, so this one move allows us to to exchange the sum and the integral. Of course, we can pull out the 1 over t, that's a constant. And what we're left with inside the integral now, instead of inside the sum, inside the integral, we have f of t e to the j 2 pi n t over t times e to the minus j omega t dt. Whew, okay. Now, one more move before we make a nice simplifying step. So we're going to have the sum still in this step. And then we're going to integrate still, but we're going to combine these two exponentials together in a specific way. We want this to be, because you can just add the exponents, right? We want this to be in the form minus j times something t, and then dt. Because if we can write it like this, then this integral will be the Fourier transform integral of f of t. So with a shift in it. So, and in fact we can write this as omega minus 2 pi n over t. Didn't give myself enough space. Just that term is over t. If I had the time, I would stop right now and show you that Mulaney stand-up comedy skit where he's drawing a happy birthday sign. You guys know this?
No.
It's so great. And he goes, so the idea is this. I won't show you the clip. It's better when you see the clip. But he's like, so, you know, when you're gonna make somebody a happy birthday sign, and you start off and you're all optimistic, and you're like, a big ass H. And then you're like, a big ass A. And then you're like, oh. A skinny P, and then another P with a hump under that P, and then a squiggly Y, and then you go to the next line and you forget everything that you learned, and then you say, a big ass B. And so anyways, I always think when I do this and I like cramp myself in here, I always think, and a big ass B. Yeah. And oh no, not have room.
Are you gonna put that on Slack?
You should do that.
I should.
Just upload it.
It's on Netflix. I don't know if there's a YouTube clip of it, but I just assume most people have the Netflix. So, okay. So this now we can recognize this term as being a very specific thing. It's the Fourier transform of f. Remember, we're trying to find the Fourier transform of f star, but we found in there an expression of the Fourier transform of f, which is a very interesting thing to find in there. And that's actually the property that we're discovering here. So what we're left with is 1 over t times the sum from n equals negative infinity to infinity of the Fourier transform of f, and then it's evaluated at omega minus 2 pi n over t. Okay? So it means that the Fourier transform f star of the sampled function little f star is a periodic repetition with frequency domain period 2 pi over t of the Fourier transform f of the continuous signal f scaled by 1 over t. It's kind of a mouthful, but it's connecting the Fourier transform of the sample function to the Fourier transform of the original function. And what it does is it essentially puts a copy of the Fourier transform of the original function at every interval 2 pi t. So for instance, this is a really quick for instance, I promise. for instance, although it is periodic and so has a trivial Fourier series, the cosine function also has the Fourier transform, and I just give it to you. I don't derive it. But notice it's a delta function. It's a Dirac delta, another Dirac delta. They're at two different frequencies. They're offset about 0 by omega naught. And omega naught is the frequency of the cosine function, the angular frequency of the cosine function. This is illustrated in the top spectrum of figure 2.4. Our expression above for f star in terms of f allows us to construct the spectrum of f star shown in the bottom spectrum. So, this is the cosine spectrum. This is 0, right? So there's a Dirac delta with strength pi at omega naught and at negative omega naught. So when you sample the cosine function and you want to look at the spectrum of it when it's sampled, then at intervals of 2 pi over t, which t, remember, is the sampling period, not related to the period of the cosine function. The period of cosine function is related to this omega naught. But you can specify the sample. You can sample a cosine at any frequency that you want, right? So what you do is at every 2 pi over t, you have a copy of that cosine spectrum that shows up. So that's why I have this color coded like that. So this is the center for the green ones, and then the red ones are centered around this one, and the blue ones are centered around 0. So we've got this sampled spectrum that arises. And this is going to come into play more later as well. We're going to start talking about aliasing next time. And it'll be fun. We'll have a good time. So I hope you enjoyed the lecture. Just lost my notes. Right. Here's to sleep.
You're not gonna stay up till 3 o'clock in the morning again, are you?